So bitwise OR is a bitwise operation that makes it so that if either of the bits that are being compared are 1, then return 1. So we need at least one digit is 1. Now let's do this with an example. Let's assume that A equals 2 and B equals 10. Now bitwise OR is represented with a vertical line like so. So for finding the bitwise OR of A and B, we do so with A, vertical line, B. Now the first step is to convert each variable or each number into binary form. And as you might know, binary form is done with powers of 2s. And we're trying to put 2 into one of these placeholders so that it's not exceeding that placeholder's value. So 2 to the 0 is 1, 2 to the 1 is 2, 4, 8, 16. 2 fits into 2 to the 1, so we'll have a 1 here. And 2 minus 2 is 0, so we've completed the binary representation for 2. So A will have 0, 0, 1, 0 as its binary representation. Now for 10, we have to find the placeholder that is immediately less than 10. And in our case, it's 2 to the 3, which is 8. So we put a 1 here. 10 minus 8 is 2, so we need to put a 1 in a placeholder that fits 2, and it would be right here. Now 2 minus 2 is 0, so we've completed the placeholder, and the binary representation is 1, 0, 1, 0. Note that I'm omitting the 0 because I'm assuming that there are 4 bits, and zeros can be extended forever. It's just like assuming it was a actual number where zeros could be forever, so I'm not representing this 0 since we don't need to. Now, what we need to do with bitwise OR is we need to find at least one digit in each vertical space. That's 1. If at least one digit in each vertical comparison is 1, then we output 1. So 0 and 0, neither is equal to 1, so we put 0. 1 and 1, both are 1, so we put a 1. 0 and 0 is 0. And then there's at least one 1 that we're comparing in 0 and 1, so we output a 1. So A ORed with B will equal 1, 0, 1, 0. And we want to find the decimal representation of this because we're using decimal values to initialize this. So in order to convert this binary to decimal, we do 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3. There's 1 in 2 to the 3 and 1 in 2 to the 1. So 2 to the 3 plus 2 to the 1 equals 8 plus 2 equals 10. So 2 ORed with 10 equals 10. Hey guys, so now we will be implementing bitwise OR in Java. So the first thing we need to do is create a class, bitwise. Notice that this class name matches our file. And now we will implement a method, and we'll make it static because we don't want to implement a new instance of the object. We just want to call the object directly in our main method. And we pass in 2 parameters, A and B, and they're both ints. And we'll simply return A vertical slash B, the bitwise OR operator. Let's just call it like that. And now we can create our main method, public static void main string args. And within our main method, we will create a variable to instantiate our method. So remember, we have to call the class that the method is in, bitwise, dot bitwise OR, and then we'll pass in two values. We'll pass in the values that I guess we'll use different values just for sake of showing that it works. And this by itself won't print anything. So if we compile this, java c bitwise.java, compile it and then run it, we won't get anything because we're returning A or B. So we have to do something like this where we print it out. And let's print out OR, so that when we compile it now, we get our OR operation. So the OR of 2 and 8 is 10. Now the bitwise AND operation is very similar to bitwise OR, the only difference being that we need both bits to have 1 in order for the output to be 1, unlike in bitwise OR where we need at least one of the bits to be 1 in order to output 1. So if we assume the same values, A equals 2, B equals 10, we can create the binary representation just like how we did for bitwise OR, where we have 0, 0, 1, 0 and 1, 0, 1, 0. And bitwise OR AND makes it so that each vertical comparison has to have both digits being 1. So neither digit is 1 here, so it's 0. Both digits are 1 here, so it's 1. Neither digit is 1 here. And then there's only one digit that's 1 here, and we need both of them to be 1, so this would also be 0. Now, bitwise AND is represented with a simple AND, so we would write it like A and B. That's a symbolic representation. And in order to find what this equals, we have to convert this to a decimal. So this is 2 to the 1, has 1 on it. So this value is equal to 2. Now the next operation is bitwise AND. So we'll do static int, and let's move this up here. Bitwise AND int A, int B, and we'll return A and B, the bitwise AND operator. And let's do the same exact thing where we do int AND equals bitwise.bitwise and A and B, but let's replace these with actual values. And if we do system.out.println AND, we should get the corresponding value of 0. So ANDing 2 and 8 will result in 0. Now bitwise XOR is interesting because it only wants one of the digits being compared to be 1. If both digits are 1, it will output 0. So if we created a short little truth table, if we compared 0 and 0 and we were using XOR, then the output would be 0. If it was 0, 1, the output would be 1. If it was 1, 0, it would be 1. And then if it was 1, 1, it's 0 because we want one of them to be 1. Now, if we use the same values that we used before, with A being 2 and B equaling 10, we find the binary representation of each one, with 2 being 0, 0, 1, 0, and 10 being 1, 0, 1, 0. And we have to find the vertical XORs for each digit. So 0 and 0 will be 0, according to our truth table. 1 and 1 will be 0. 0 and 0 will be 0. And then 0 and 1 will be 1 because we need one of the digits to be 1 in order for XOR to output true. And true is 1. True equals 1. False equals 0. And so we have 1 here. And that's bitwise OR. And bitwise XOR is represented with a exponent or caret B. And that's how you symbolically represent it in code. Now let's do static int bitwise XOR. and we'll do int a, int b, same exact implementation, return a caret b, the bitwise XOR operator. And let's just copy and paste this and change it a bit. So instead of and, we'll do XOR, bitwise XOR, print out XOR. And if we do this, we now get 10 as our XOR. Next thing that we have to do for bitwise is bitwise complement, which uses tilde a, and this is a unary operator in that we're only comparing one number. So we can do bitwise complement for a, and we can also do a separate one for b, but just know that the output is the reverse of whatever we have currently. So we know that a is equal to 2, b is equal to 10. So a has a 0, 0, 1, 0 representation. Now if we want to find the complement of a, we have to simply reverse the bits. So we change all the zeros to ones, and we change all the ones to zeros. So this would be 1, 1, 0, 1. And we just complemented a. Now if we want to find the decimal value, we do 2 to the 3, 2 to the 2, 2 to the 1, 2 to the 0. 1, 1, and 1 for 2 to the 3, 2 to the 2, and 2 to the 0. So we have 8 plus 4 plus 1 equals 13. And that is the complement value of 2. Now if we did the same thing for b, we can do tilde b equals 1, 0, 1, 0, or sorry, b equals 1, 0, 1, 0, tilde b equals 0, 1, 0, 1. And this is 2 to the 0, 1, 2, so 4 plus 1 equals 5. So the complement of b is 5. Now we'll go into signed right shift operator and unsigned right shift operator. So there's two types of shifts. There's right shift and left shift. I won't be going over left shift because once you understand right shift, left shift is simply the opposite. So let's do signed right shift, and let's assume instead of using variables, we'll do -6 right shift signed 2 spaces. So let's say we have to shift the bits in -6 by 2 spaces. And in order to do this, we have to convert each one into binary, or sorry, we don't convert this into binary. We only compare the -6 into binary. And then we move the bits to the right by 2. So -6 is represented in binary by finding the positive and finding the complement and then adding 1 to the complement. And this is how negative numbers are represented in binary. So just to review, say we have -2. In order to find the binary for -2, we have to find the positive binary value for 2, which is 0, 0, 1, 0. And in order to implement the negative, we have to find the complement of this. So 1, 1, 0, 1. And then we have to finally add 1. So 1 plus 1 is 0. And we add that 1 here. And then 1, 1. So our binary representation for -2 is 1, 1, 1, 0. So we're going to do the same thing for -6, where we have to find the positive binary representation for 6, find the complement, and then add 1. So 2 to the 0, 2 to the 1, 2 to the 2. We have 6 here. So 2 to the 2 will fit into 6. So that's 4. So we'll put a 1 here. 6 minus 4 is 2. So we have to find which one will fit into 2. And it's this one. And then the rest are 0. So this is the binary representation for 6. Now we have to find the complement of 0, 1, 1, 0, which is simply reversing the bits. So 1, 0, 0, 1, and then we add 1. So 1 plus 1 is 0. Put the 1 in the next place. 1 is down here. And our representation is like that. Now what we need to do is we have to right shift, but also keep the most significant signed bit there in our solution. So one thing to understand is that if we extended 1010 to like 16 bits, it would look like 1111 1111 1111 1010 because we're sign extending this 1. So if we had to move this 2 places to the right, we have to move it like a conveyor belt where 0 goes into the machine and disappears, and we replace each digit that's gone into the machine with a 1 because we're sign extending. We're adding 1 to the end. And just to review what sign extending is, 1 will be sign extending values that are negative, and then 0 will be sign extending values that are positive. So we have 1 here because it's -6 and not 6. Now, shifting 2 places to the right means that we have to delete the least significant bit and add 1 to the most significant bit. So if we do 1 shift to the right, we'll get 101, and this 1 will be here, and then the rest will be 1s. So that's 1 shift. Now we have to do another shift. So we move this 1 into the machine, making this bit the least significant bit, and then we add a 1 to the end. So it'll be 0, 1, 1, 1, this 1 moving here, then 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. And this is our binary representation of -6 right shifted, signed right shifted to 2 spaces. Now if we wanted to find the equivalent value, decimal value for this, we would simply have to notice that all of these are just sign extended, so we only need to find the decimal value of 1110. So in order to find the decimal value of 1110, we have to do the reverse of what we did when we turned the positive binary to negative by finding its complement and adding 1. So what we have to do is, if we have 1110, we reverse again, 0, 0, 0, 1. We add 1, so 1 plus 1 is 0. And our positive representation is 0, 0, 1, 0. So if we convert this to decimal, we get 2. So that means that 1110 is -2. So our right shift 2 spaces ends up being -2. Now we can finally do unsigned and signed. So let's start with signed. Static int signed right shift int a, because this is a unary operation, and we will return a 2 of these instead of 3, because if we use 3 it would be unsigned. And now we can try and output this. So int, let's call this signed equals bitwise dot bitwise, signed right. And let's make this, how about we make this -6, and then we system.out.print ln signed, and if we output this, we get -2, which is exactly what we got when we found this by hand. Now, right shift unsigned is kind of wacky in that you have to remember that instead of extending extending the number that is leading our binary representation, we're always going to add 0 to our binary representation whenever a least significant bit is leaving our representation. So this will make more sense when we actually do it, but let's use the same numbers that we used from this assigned right shift operation where we did -6 right shift 2. Now this is going to be unsigned, and it distinguishes from signed in that there's another extra right shift operator. So our first step, just like signed, is to convert -6 to binary, and for the sake of time we'll just see how we implemented it here, and we converted it to binary, we complemented it, and then we added 1. So -6 is 1 0 1 0, and then we want to shift this 2 spaces to the right. Now this can be sign extended to 16 bits, so let's do it just for clarity. So we have this as our 16-bit representation, and now we have to do the same conveyor belt method where we take out the least significant bit and add a 0 to the most significant bit instead of 1. So no matter what number is leading our representation, we have to always input a 0 into the most significant bit. So this means that we'll have 1 0 1 since we're taking out the 0, and 1 0 1 is now our least significant bits, and we have this as our representation. Notice how 0 was added to the most significant bit and not 1, unlike how we did for the signed right shift operation. Now this is the first shift. Now we have to do it one more time since we did -2 shifts to the right, and we delete the least significant bit, put 1 1 0, shift this 1 over here, and then the rest of these are going to be 1. And then here we're going to have 1 1 0 0 because we're adding a 0 to this binary representation again. So we're left with this number. Now, for the sake of time, I'm not going to actually compute what this equals because this is actually a very big number, because as you can tell, 2 to the 0 is this, so 2 to the 1 is this, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, 6, 7, 8, 9, 10, 11, 12, 13. So the most significant bit is 2 to the 13, which is, if I pull out my calculator, 8,192. So this is a very big number, and because of this, I calculated this beforehand, and this will output 16,382, and this is the number that comes out of the unsigned right shift operation, where we shift 2 places and we replace the places that we've lost with zeros. And we have to account for all 16 bits because we have zeros right here, and the number isn't signed extended anymore since these aren't 1s. If these were 1s, then we would only have to find the value of this because the rest of these values were sign extended from this bit. So that is the by hand representation. And when we enter the Java portion where we implement unsigned right shift operations into the compiler, we'll find something interesting. So now let's do static int unsigned right shift and do int a. Return a is we'll have 3 instead of 2 from signed, and we will do the exact same thing. Let's copy and paste this, make this unsigned, and we called this unsigned right shift, and we will print unsigned. Cool. And if we run this, we get a huge number, and this number is because we are using 32 bits. So if we look up how many bits a number will use for an int in Java, we get that 32 is the default data type, which means that instead of when we did this by hand, I'll make a comment. When we did this by hand, we only used 16 bits. So we did this like, I forgot the exact binary, but we did it like that, right? Now this is 16 bits. But what we're seeing here is that, and that's why we got like 13,000 something. That was the decimal equivalent of these 16 bits. But what we're seeing here is that we use 32 bits. So we're actually effectively doubling this amount. So we're creating that, and that's 32 bits. So this would be like 1 probably. This would all be 1 We're actually doing 32 bits, and these two most significant bits are 0 and 0 respectively. So if we found the decimal equivalent of this 32 bits, we would probably get a huge number like this. And that's why we get such a big number, and we don't get the number that we got when we did this by hand when we did 16 bits. And it's because by default, most modern compilers will use 32 bits. Now let's make sure that this is actually a thing and I'm not just saying it. By instead of making this int, let's actually make this long. So if you look up long, it'll be 64 bits. So if I look up long, it'll have 64 bits. So we should get an even bigger number when we substitute these with long, type long. And then this would shift to long, and that's it. And now if we compile this, we get an even bigger number, and this will be magnitudes larger than before because we are we're doubling the size of this by another amount. So that makes sense why the long number would be even bigger. We did all the implementations for AND, XOR, signed, and unsigned. I guess we can do complement too. Complement is very straightforward as well. Static int complement int a, return that, and then if we run it, we do int compla, let's do comp equals bitwise dot complement, let's do 3, let's do 2, and then system dot out dot println comp. We will get the complement of this number, which is -3. And there you have it. We've covered the very basic but very crucial and essential bitwise operations, as well as the signed and unsigned right shift operations. Just understand that there's also unsigned left shift and signed left shift, which I haven't covered for sake of time, but just know that they look exactly like signed right shift and unsigned right shift, in that if we did signed left shift, we would return a 2 like that, and same here, we would do a 3 of those 2. And this simply means that instead of making the most significant bit zeros, we make the least significant bit zeros, and we shift everything to the left instead of shifting everything to the right. So it's pretty self-explanatory if you understand what signed and unsigned right shift do. And that's pretty much it. Let me know how your data structure journey is going, and hope to catch you in the next video. Peace.